From sparks to spectra, the periodic table story, the cosmic ingredient list. Take a moment to look at the world around you. The chair you're sitting on, the screen you're watching, the very air you are breathing. It all seems infinitely complex and varied. Your phone, for instance, is a marvel of engineering, containing dozens of materials. Its brain is a chip of hyper-pure silicon. Its battery is powered by lithium, and its circuitry is connected by traces of gold and copper. The coffee in your mug gets its character from a complex blend of organic molecules, all woven from atoms of carbon, hydrogen, and oxygen. Even you are a collection of these fundamental ingredients, mostly oxygen, carbon, and hydrogen, with trace amounts of dozens of other substances that make life possible. All of it, the living and the non-living, the manufactured and the natural, seems so incredibly different. Yet, from the brightest, most distant stars to the smallest microbe on Earth, everything in the universe is constructed from a surprisingly small set of fundamental ingredients. These ingredients are called the chemical elements. They are the building blocks of all matter, the alphabet from which the entire story of the cosmos is written. We organize this cosmic ingredient list into one of the most powerful icons in science, the periodic table. But this elegant chart is not an ancient artifact discovered in a tomb. It is the result of one of the greatest detective stories in human history. A story that begins not with science, but with philosophy. Over 2,000 years ago, in ancient Greece, thinkers began to ponder the fundamental nature of the world. The prevailing theory, championed by philosophers like Empedocles and later codified by Aristotle, was that all matter was composed of just four essential substances: earth, water, air, and fire. This idea was intuitive. It was based on direct observation. A burning log, for example, seemed to contain all four elements. It was solid like earth, it hissed with water, smoke rose like air, and it produced fire. These elements weren't just substances, they were principles, imbued with qualities like hot, cold, wet, and dry, and their interplay was thought to explain all of reality. But there was a competing, more radical idea. Thinkers like Leucippus and his student Democritus proposed that if you could cut a piece of matter in half, and then in half again and again, you would eventually reach a point where it could not be cut any further. They called these final indivisible particles atomos, the origin of our word atom. For the atomists, the world was made of these tiny, solid particles moving through an empty void. The different properties of materials were explained by the different shapes, sizes, and arrangements of these atoms. It was a purely mechanical universe. These were profound philosophical insights, but they remained just that: ideas. There was no way to test them, no experiment to prove one right and the other wrong. For nearly 2 millennia, Aristotle's four-element theory held sway. The next major step came from an unlikely source: the mystical and secretive practice of alchemy. Flourishing from late antiquity through the Middle Ages and into the Renaissance, alchemists inherited the Aristotelian framework. They believed that by manipulating the elemental qualities of matter, they could achieve extraordinary feats. Their most famous goal was chrysopoeia, the transmutation of base metals like lead into pure gold. They sought the philosopher's stone, a mythical substance that could perfect matter and grant immortality. While their theories were steeped in mysticism and allegory, their methods were surprisingly practical. In their relentless pursuit, alchemists became masters of the laboratory. They invented and refined crucial techniques like distillation, sublimation, and crystallization. They developed the glassware that would become the staple of the modern chemistry lab: beakers, flasks, and retorts. And in the process of trying to break matter down into its supposed four elements, they accidentally discovered new, fundamental substances that resisted any further simplification by their methods. They isolated elements like antimony, arsenic, and bismuth. In 1669, the German alchemist Hennig Brand, in a futile search for the philosopher's stone in urine, instead discovered phosphorus, a substance that glowed eerily in the dark. The alchemists never found the philosopher's stone. They never turned lead into gold. But their failures were more valuable than they could have known. They had unwittingly begun to populate the true list of cosmic ingredients. They laid the empirical groundwork for a revolution in thought, a shift from a world of 4 mystical elements to a world of many, distinct, and discoverable chemical elements. Their work marked the dawn of early empiricism, setting the stage for the birth of modern chemistry. The quest to understand these new substances, to measure them, count them, and find the hidden order among them had just begun. Section 1. From Ancient Ideas to Burning Questions. Our story begins long ago, in a world without laboratories or scientific instruments, but one filled with a profound and universal curiosity. Before the first equation was ever written, humanity looked at the world, the rocks, the rivers, the stars, and asked a fundamental question. What is all this stuff made of? This question was not confined to a single time or place. In ancient India, the concept of the Pancha Mahabhuta, or 5 great elements, earth, water, fire, air, and ether, provided a framework for understanding the cosmos. In China, the theory of Wuxing described 5 phases: wood, fire, earth, metal, and water, whose interactions explained everything from seasonal changes to human health. These were not just lists of substances, but sophisticated systems for explaining change and process. But it was in the bustling cities of ancient Greece that a particular line of inquiry took hold, one that would directly shape the course of Western science. Early thinkers, trying to make sense of the overwhelming variety of the world, proposed that everything was made from just a few fundamental substances. Philosophers like Thales of Miletus argued that all was derived from water. Anaximenes proposed air, and Heraclitus, fire. Around 450 BC, the philosopher Empedocles synthesized these ideas, suggesting that everything was a combination of 4 core components, or roots: earth, air, fire, water. This idea was simple, elegant, and made a certain kind of intuitive sense. It was later championed and expanded by Aristotle, who paired these elements with qualities: hot, cold, wet, and dry. In his view, one element could transform into another by changing its properties. This framework, which explained observable phenomena in a logical, self-contained system, would become the undisputed authority on the nature of matter for nearly 2 millennia. A burning log, for example, could be perfectly explained within this system. It releases smoke, air, sap, water, ash, earth, all driven by its inner fire. It was a complete and satisfying explanation, built entirely from observation and reason. In its ambition to classify the building blocks of reality, this was humanity's first attempt at a periodic table. For nearly 2,000 years, these classical elements, along with the mystical pursuits of alchemy, dominated human thought about matter. Alchemy, which flourished from Hellenistic Egypt through the Islamic Golden Age and into medieval Europe, inherited Aristotle's ideas. Alchemists, often seen as secretive magicians, were in fact early and often obsessive experimenters. They believed that if all matter was composed of the same few elements in different proportions, then it should be possible to change one substance into another. They mixed, heated, distilled, and calcined, developing a vast body of practical knowledge. Their most famous goal was chrysopoeia, the transmutation of base metals like lead into noble ones like gold. To them, this was not just about creating wealth, but about perfecting matter, bringing it to its most incorruptible state. While their ultimate goal was never achieved, their tireless work led to the discovery and isolation of new substances, like phosphorus, arsenic, and antimony. They invented and refined crucial laboratory techniques and apparatus, distillation, filtration, crystallization, that are still used today. They were the first to get their hands dirty, moving beyond pure philosophy and beginning the slow, messy, and often dangerous process of experimental science. But a major shift was needed. The world needed to move from thinking about what should be true, based on ancient texts and philosophical ideals, to discovering what is true through careful, repeatable observation. The Renaissance sparked a new spirit of inquiry, but it was during the scientific revolution of the 17th century that the old ideas truly began to crumble. A new generation of thinkers, armed with a growing skepticism and a desire for empirical proof, started asking different questions. Among them was the Irish natural philosopher Robert Boyle. In his 1661 book, The Skeptical Chymist, Boyle launched a systematic attack on the Aristotelian and alchemical traditions. He argued that the four elements, and the alchemists' three principles of salt, sulfur, and mercury, failed as universal components. They couldn't be isolated from most substances, especially not from metals like gold. He then proposed a new operational definition for an element, a simple, unmingled substance that could not be broken down into anything simpler by chemical means. This was a revolutionary idea. It was not based on intuition or philosophy, but on a practical, testable criterion. A substance was an element only if no known chemical procedure could decompose it. Gold was an element because no one had ever succeeded in breaking it down. Water, by this definition, was not necessarily an element because its true nature had yet to be proven through experiment. This shift in thinking set the stage for the true birth of modern chemistry. The goal was no longer to impose a philosophical system onto nature, but to let nature reveal its own structure through experimentation. The focus moved to measurement, precision, and repeatable experiments. The alchemist's workshop, filled with allegory and mysticism, began to transform into the chemist's laboratory, a place of quantification and rigor. The key question was no longer about mythical transmutations, but about tangible properties. What is a substance made of? What is its weight? How does it combine with other substances, and in what specific, measurable ratios? The old world of alchemy and philosophy, which had reigned for 2 millennia, was giving way to a new world of data and evidence. Boyle's definition had provided the intellectual toolkit, but the work itself was just beginning. The quest for the true elements had begun in earnest. It would be a painstaking process of discovery, fought not with spells and incantations, but with scales, furnaces, glassware, and the relentless power of human reason. The age of qualitative description was ending. The age of quantitative analysis was dawning. Section 3. A Journey Through Time. The story of the elements is the story of everything. It is a narrative written not in words, but in the very substance of the cosmos. To truly understand this epic, we must become historical detectives, following the path of discovery precisely as it happened, step by step. Our journey will be a timeline to the truth, a chronicle of human curiosity and intellectual courage. We will see how each new piece of this grand puzzle was unearthed, often by accident, sometimes through sheer genius, and how it was meticulously fitted into the bigger picture. This is not a simple linear tale, but a complex web of dead ends, fierce debates, and brilliant breakthroughs that ultimately revealed the fundamental order of our universe. We begin in the crucible of the chemical revolution of the late 18th century, a time when the mystical art of alchemy was finally giving way to the rigorous science of chemistry. Here we meet Antoine Laurent de Lavoisier, a meticulous French aristocrat who would become the father of modern chemistry. Lavoisier's revolution was not one of new discoveries alone, but of a new philosophy. His unwavering principle was that of measurement. By precisely weighing reactants and products in sealed vessels, he demonstrated the law of conservation of mass, proving that matter is not created or destroyed in a chemical reaction, only transformed. This simple but profound insight allowed him to systematically debunk long-held theories like phlogiston. In 1789, he published the first modern list of elements, substances he defined as being unable to be broken down by any known means of chemical analysis. It was a foundational first step. The revolution continued with the discovery of invisible gases, paving the way for the English schoolteacher John Dalton. In the early 1800s, Dalton resurrected the ancient Greek idea of atoms, but with a crucial scientific update. He proposed that each element consists of a unique type of atom, each with its own characteristic weight. He theorized that chemical reactions were simply the rearrangement of these atoms. This atomic theory gave scientists the first quantitative clues about the fundamental nature of matter. From there, our path leads into the 19th century, a time of explosive discovery fueled by the relentless engine of the Industrial Revolution. Science was no longer a gentleman's hobby. It was becoming a professional, industrial, and national endeavor. We will witness how the strange new force of electricity, harnessed in the form of the voltaic pile, became a powerful tool for tearing substances apart. Chemists like Davy at London's Royal Institution realized that if chemical forces held compounds together, perhaps a stronger electrical force could pull them apart. In 1807, by passing a powerful current through molten potash and soda, Davy succeeded where centuries of chemists had failed. He isolated two fiercely reactive new elements, potassium and sodium. The floodgates were open. In the following years, electrolysis would be used to discover a host of other elements, including magnesium, calcium, and barium. Then, as the list of known elements grew, a new puzzle emerged. How could one study and identify them all? For the next breakthrough, scientists turned their attention from matter to light itself. In the 1850s, Robert Bunsen and Gustav Kirchhoff developed the spectroscope. They discovered that every element, when heated to incandescence, emits a unique signature, a precise pattern of colored lines, a secret barcode written in light. This was the birth of spectroscopy, a powerful analytical technique. This revolutionary tool allowed them to discover new elements like cesium and rubidium, but its power extended far beyond the workbench. By analyzing the light from the sun, they found the same spectral fingerprints, proving the sun was made of the same elements found on Earth. They even discovered an element in the sun's spectrum, helium, nearly 3 decades before it was found on our planet. Spectroscopy turned the entire cosmos into a laboratory. The final act of our story will take us into the strange and wonderful world of the 20th century. The great questions of the 1800s had been answered, but the answers only led to deeper questions. What gave each element its unique weight? Why did they emit their specific spectral barcodes? To find out, we must dive deep inside the atom itself. We will follow the pivotal experiments that shattered the idea of the indivisible atom. We'll see J.J. Thomson's discovery of the electron, Ernest Rutherford's discovery of the tiny, dense nucleus, and finally James Chadwick's identification of the neutron. The atom was revealed to be a complex system of subatomic parts. This journey into the subatomic world led to the development of quantum mechanics, a bizarre but stunningly successful new theory. It would be the strange rules of the quantum realm, the behavior of electrons in shells and orbitals, that would finally provide the ultimate, fundamental explanation for why the periodic table has the shape it does and why it works the way it does. And at the heart of this entire story stands one of science's greatest visionaries, Dmitri Mendeleev. In 1869, the Russian chemist organized the 63 then-known elements into his famous table, arranging them by atomic weight and grouping them by shared chemical properties. His genius was not just in the arrangement, but in his audacious confidence to leave gaps for elements that had not yet been discovered and to predict their properties with uncanny accuracy. We will see how his incredible foresight was eventually and beautifully explained by quantum mechanics. This story matters because it is the absolute foundation of our modern technological world. Understanding the elements is crucial for everything from creating life-saving medicines and novel materials to fabricating the computer chips that power our digital age and developing the technologies needed to build a sustainable future. The periodic table is not a dusty, static chart on a classroom wall. It is a living, predictive map that continues to guide innovation and discovery. It is the most compact and meaningful summary of scientific knowledge ever created. As we trace the creation of this icon of science, we will reveal the ultimate story of human ingenuity. It is a 2,000-year quest, from the philosophers of ancient Greece to the particle physicists of today. A relentless drive to read the cosmic recipe book and, in doing so, to understand our own place in the universe.